Okay, this is Engineering 120 Lab 6, and here's my circuit I built in lab. And this is Engineering 120 Lab 6, section MO2, and I am Matthew Goodenough. And here I chose my resistors. Resistor 1 is going to be 1.975 ohms. Resistor 2 is 326.6 ohms. Resistor 3 is 0.9. 4 is 0.5 kilo ohms, and 1.197 ohms, and these are the values it's almost close to, but it has some percent error in there, but that's okay. And then here you measure each value with your multimeter using ohms and finding its resistance. You do that for each one. Like for this one, that one's the 1 kilo ohm. The next resistor is the 500 kilo ohm, 500 ohms, 510 ohm that's supposed to be. You do the same thing for all of them, and then you get those values. Now we go and measure our circuit. We're gonna find the currents, and we do our equivalence, which we know those two are parallel, so we do 1 over R1, R2 to the -1. You get your equivalence. We solve for equivalent circuit. Our goal is to find IS, which is 5.35 milliamps, and we can check this in our circuit. Opening the circuit and finding the current through the system. So I'll show the volts. So here I have my voltage source is 10.5 volts. We measure this on our multimeter. Sorry, you have to adjust it a little bit. Pain in the ass. Let's see. There it is, 10.5 volts, and that's from our voltage source. Now we're going to measure current, so we have to break this circuit and switch our multimeter. So from our calculations of equivalent circuits, getting it into series, adding those all together, we get equivalence of there. Then we look for our IFS, and here we've calculated to be 5.35 milliamps. So here it measures about like that. I think the voltage changed a little bit on that, which it will. My circuit's a little crooked, but that's fine. But you should measure it and you should get the same milliamps. In this case we did. And you have to open your circuit and then go to DC current, and it flows through the multimeter. And then you use the voltage division and current division to find you the rest of the currents for I1 and I2 in this circuit. And we found it to be 0.759 milliamps and 4.59 milliamps. And then you do the same for the voltages at the resistors. And then to measure them, so to find the voltage, the current at different resistors, I'll just do 2. Let me set them up here. So here we got Oh, current 4.56 milliamps. Here we get the same reading, and this is how you open the circuit for those parallel circuits. You put it on the other section of the breadboard, go through, and it goes back through. Then that's how you find your current, and that's what we calculated before in our hand calculations. As you see right there, 4.59, and we got 4.56. It's a little difference. There's some error in there. Normally it's the voltage because it like varies. Let me set up the circuit. And I'll do the current at the last resistor because it's easier to set up. So current at the last one is 5.23 milliohms, which are exactly the same one. So we're getting the same current at the end result. And to measure voltage, you just measure voltage across your resistors. So now you just measure your voltage across your resistors. Top of the circuit. I swear it works on the ones that I don't. Oh, that's why. So here, voltage at resistor 3 is 5.26. We get 5.26, and we also get that in the multimeter. Then I'll do the last voltage 5. You get 1.056 for our last voltage, and here we get the same answer. And that's how you measure your resistance, your voltages on each one. And that concludes lab 6. We found the equivalent resistance of a complex circuit. We also measured those values to check it within our breadboard, our resistors, our current, and our power supply. And that's it. That concludes lab 6. This is Matthew Goodenough, Engineering 120, section MO2. Thank you for listening, and that is my lab. Bye.